In our previous session, we had seen about thrust required. Let us see thrust available in this session. Thrust required (TR) is dictated by the aerodynamics and the weight of the plane itself. It is an airframe-associated phenomenon. In contrast, the thrust available (TA) is strictly associated with the engine of the aeroplane. It is the propulsive thrust provided by an engine-propeller combination, a turbojet, a rocket, etc. Reciprocating piston engine with propellers exhibit a variation of thrust with velocity. Thrust at zero velocity is a maximum and decreases with forward velocity. At near sonic flight speeds, the tips of the propeller blades encounter the compressibility problems. The thrust available rapidly deteriorates. On the other hand, the thrust of a turbojet engine is relatively constant with velocity. These two power plants are quite common in aviation today. Reciprocating engine-propeller combinations power the average light, general aviation aircraft, whereas the jet engine is used by almost all large commercial transports and military combat aircrafts. Consider a jet aeroplane flying in level unaccelerated flight at a given altitude with a velocity v1. Point 1 on the thrust required curve gives the value of the thrust required for the aeroplane to fly at velocity v1. The pilot has adjusted the throttle such that the jet engine provides thrust available just equal to the thrust required at this point. This partial throttle TA is illustrated by the dashed curve. If the pilot now pushes the throttle forward, the higher value of TA, the aeroplane will accelerate to the higher velocity. If the throttle is increased to full position, maximum TA will be produced by the jet engine. In this case, the speed of the aeroplane will further increase until the thrust required equals the maximum thrust available. It is now impossible for the aeroplane to fly any faster than the velocity at point 2. Otherwise, the thrust required would exceed the maximum thrust available from the power plant. Hence, the intersection of the thrust required curve dependent on the airframe and the maximum thrust available curve dependent on the engine defines the maximum velocity Vmax of the aeroplane at the given altitude. To calculate the maximum velocity of CJ1 at sea level, power plant of CJ1 consists of two turbofans which is of 3650 lb of thrust. Hence, we get thrust available as 2 into 3650 is equals to 7300 lb. The thrust required is equals to thrust available, which means Vmax is equals to V infinity is equals to 975 feet per second from the graph. At sea level, the speed of sound is 1117 feet per second. Hence, the maximum sea level Mach number is given as Vmax by A, which is equals to 975 by 1117, which gives you 0.87, which is the maximum Mach number. I hope you would have understood thrust available. Let us move on to power required in the next session. Thank you.